Okay, this is the proof of online mirror descent. From the definition of online mirror descent, we can write down eta vt is equal to gradient of pi wt minus gradient of pi wt plus 1 half, right? So the first inequality comes from the fact that ft is convex function, and then the second line comes from this property. Okay, so just for notational convenience, let's use L, capital L notation to denote the difference between Bregman divergence between UN WT and UN WT plus 1. Then from the definition of Bregman divergence, this subtraction equal to this. Okay, there is no difficult math. I just write down the definition of Bregman divergence. That's it. Okay, so since WT plus 1 is argument of Bregman divergence between W in our hypothesis class and WT plus 1 half, for any U in our hypothesis class, we have this inequality. Here I use the fact that pi is convex function, and so the Bregman divergence is simply convex as well. So this is the gradient of Bregman divergence at point WT plus 1. Okay, this is equal to gradient of Bregman divergence at point WT plus 1. So this is equal to this. And since Bregman divergence is also convex and which is optimized at point WT plus 1 with any U inside of hypothesis class, we have this inequality. This is just property of convex optimization. Right. Then, using this fact that we can we first simply write down this using adding and subtract the same term, this one. And from this line, we can make this inequality use this inequality. Okay, so we can simply replace the gradient of pi wt plus 1 half and the inner product between this and wt plus 1 minus u by gradient, the inner product between gradient pi wt plus 1 and wt plus 1 minus u, use this inequality. Okay. Then from the definition of L, we can rewrite this line like this. Okay, there's no difficult math. I just write down the last equation using the definition of L. Okay, so far so good. So since pi is convex, we can also say this. So pi wt minus pi wt plus 1 minus inner product between gradient of pi wt plus 1 half and wt minus wt plus 1, which basically equal to this using the definition of Bregman divergence. And since pi is convex, we know that this term is negative. Okay, so this is upper bounded by this, right? So why I upper bound this? This is the term here. Alright, so in the first page of proof, we know that the sum of loss difference is upper bounded by this relationship, and this is upper bounded by L, this is L plus the Bregman divergence between WT and WT plus 1/2. So since this is Bregman divergence between U and WT minus Bregman divergence U and WT plus 1, when we add up from T1 to capital T, subtracting, and we know that Bregman divergence is always positive, non-negative. It can be 0 when both terms are the same. Anyway, so we upper bound this part by the Bregman divergence between U and W1, and then the remaining term. That's it. Regret is upper bounded by 1 over eta times Bregman divergence between U and W1 plus 1 over epsilon, 1 over eta, 1 over step size, times summation of Bregman divergence between WT and WT plus 1/2.